So, I thought I'd start out with a little sort of primer in solid mechanics, stress, strain, and elasticity, because I really don't know what everybody's background is, and there are parts of it that are a bit thorny. So it doesn't hurt just to be all reminded. And then I have a section where I kind of talk about some of our experiences and how to get data that is interpretable or easy to interpret. Then I was going to talk a little bit about sample length, and then I'll talk about how we interpret our diffraction data. And I think Caleb is going to talk about the other method, the Sings method. And then Taryn is here and she's going to talk about ultrasonic data. Okay. So can everybody hear me well? Are we don't have technical issues, right? Okay.
Yeah, very clear.
Okay.
Very clear.
So I'm going to start talking about elasticity. Um, And one might think, why do we care about elasticity? Because it's something I learned very early in graduate school is that rocks deform ductily and elasticity is just not important. But for doing synchrotron work, it's extremely important. And that's because the changes in the d-spacing that you are measuring are due to just the elastic effects. We cannot see dislocations. Plasticity is essentially inferred from the decrease in the stress states in the material below what you'd expect if it was being completely elastic. So we'll talk about what stress is briefly, just as a reminder, and some things about elasticity. Okay, so as hopefully you all know, I can kind of see you all. Do you all know that stress is a tensor? The people in the back? Okay, good. So stress is a tensor. It describes forces on a body and basically, just some random body, random forces on it. You can characterize it with the stress tensor, which we often, it's a box of 9 numbers. It's diagonally symmetric, so you only really need 6. You can diagonalize the stress tensor so that you have, oh, it should say eigenvalue floating around over there, but it got lost. Okay, so sometimes these guys are called eigenvalues when you diagonalize a tensor. We can also calculate the mean stress, which when there's no deviatoric stress is also the pressure, which is the diagonal divided by 3, the sum of the diagonal divided by 3. Okay, so hello. Uh, did it move? No. Okay, there we go. So, oh, there it says eigenvalues. That's right. So, another thing we can do is calculate the differential stress or deviatoric stress or a bunch of different ways to do this. Um, a generalized one is the equivalent von Mises stress. So basically, you're just taking the differences between the body diagonals and squaring them and subtracting them from each other. So okay, so then on to elasticity. So elasticity is the thing that allows us to relate stress and strain. And a very simple modulus is the Young's modulus. So a little diagram from Wikipedia, and it shows that the Young's modulus is the stress divided by the strain. So in the little diagram, you can see the stress is force over area, and the uniaxial strain is delta x by x. And then Poisson's ratio, you're simply looking at the expansion of the body as you compress it. Or it can, if you're, this is a diagram for actually pulling on it, then it will shrink in on the sides. So basically, the Poisson's ratio is the amount of change in y divided by the amount of change in x. Okay, and then of course there's the bulk modulus, which is looking at how the volume changes as a function of pressure, and these are all related. Okay, and then lastly is the shear modulus, which is we're just looking at how difficult it is to shear. And all of those moduli can be related to each other, and there's this nice table that shows the the way that you can calculate the bulk modulus. If you have two of any of these, you can get the rest of them basically. Okay, so now that was all for a material that's completely isotropic. But the materials we work with, unless you're deforming glass, are anisotropic, which means that their properties are different in different directions. And so for a crystal, when before, like the little box, it was showing, oh, you pull on the box and it just gets longer. If you compress the box, it gets shorter. But for a crystal, you can compress it and it can kind of kick off to the side or do something different. So, and that's because of the crystal lattice. So the elastic constants for single crystals are these guys, the CIJKL. So it's a fourth rank tensor, and it's actually much larger than this because you would have, notice this says CIJKL, but down in little box, I've got the elastic constants, and I've listed them as Cij, and that's because there's this tensor notation that allows us to compact this. And like I said, with stress, it's symmetric about the body diagonal. So the fourth rank tensor actually has like, I think 90, 80, 91 or something, some horrible number of constants. And fortunately, you can kind of ignore most of them because they reproduce each other. So anyway, so we have these, what we call it CIJs. They are the single crystal stiffness tensor. And you can, just do hear that. And you can also express this in terms of the single crystal compliances. So this is just, instead of here, you can see it's the strain divided by the compliance times the change in stress. And for the other formulation, the stress is equal to the change in strain times the single crystal elastic constants, the CIJs. Okay, so those are two formulations that you see. And if you want to think about like this from a more intuitive framework, I like to start with muscovite. You can think about the muscovite structure. It's made of sheets of octahedra with the tetrahedra on either side. And if you had mineralogy or something, you know that the tetrahedral bonds are very strong. And so we have a structure that's highly anisotropic. We have sheets with very strong bonds in the plane, and then they are separated by much larger atomic sites where we can put big cations. And so if you think about it, it's going to be really squishy in the vertical direction and not very squishy in the horizontal direction. So this is expressed over here where we have the effective Young's modulus along the c-axis, which is vertical, is quite small, right? So it's compliant, and it's much stiffer along the A or B axis here. Okay, so this is maybe an extreme for minerals, but it is not unusual. So here are little kind of figures that show the variation in the Young's modulus as a function of crystallographic orientation for olivine, which looks kind of like a football, quartz, which is a very strange shape. I don't know what you would call that, but it's kind of got these little triangular lobes that are opposite on the bottom side. And then you can see pyroxene, which is kind of like a little squashed pillow too. Okay, so, and I mentioned here that these guys, this one, the quartz is drawn by something called SCEMA, which I'll talk about later. And the other ones are from a program called Anisoviz, which you can get as a plugin for MATLAB. Okay. So because the elastic tensor is related to the crystal lattice, the population of the elastic tensors are also related to the crystal the symmetry, right? So for an isotropic material that has no symmetry, this is like a glass, you basically have two elastic constants. So you can see the little diagram here. It's got these guys, these three are linked and these three are linked. And then the x's can be related to the other guys through these little equations down here. So just like we talked about earlier, you have two independent elastic constants for an isotropic material. For a cubic material, you have three. So there are these three, and those three are all the same. Then as you go to hexagonal, things start to deteriorate, so to speak. So you can see there's one, two, three, four, five independent elastic constants, and all the little dots are zeros. So for trigonal, things start to get a little bit messier. Now we have um, elastic constants are equal but have an opposite sign, which is what that little diagram up there means. And it continues on as we go through tetragonal. Or rhombic has, more, monoclinic has more, and triclinic you have 21. Okay, so you just need to know this because when you're working with the single crystal elastic constants, you really want to know how many you have. And that depends on the mineral you're working with. Okay, so now um, we're going to think about this rather complex situation where you have crystals that have different elastic constants in different directions. And now you may have more than one crystal in your material. So here's kind of like a diagram of some grain boundaries. And within each grain in the material, I have put a little cartoon to show what its elastic tensor is looking like. So the question is, how do you figure out what the overall behavior of this material is? And this is a sort of age-old problem, and there are three different solutions, and I'm going to go through these fairly quickly. Can I see it? Like, it's so hard to teach from far away. Can I see like waving of hands if this is like totally boring and you've seen this a million times before? Okay, how many people are totally overwhelmed and have no idea what I'm talking about? Matt. Okay. All right. So hopefully we're somewhere in between. I encourage you to sort of figure out some way to stop me and ask questions. It's probably best to do that rather than have me droning on and having lost everyone. Okay. So now I'm going to talk about three ways of figuring out what the bulk properties of this material are going to be. Royce isostress, Voigt isostrain, and a self-consistent formulation. All right, so the Voigt isostrain is an approximation that answers the question of what is the modulus of the Young's modulus of the entire body going to be if we say that it has all of the parts enjoy the same strain. So that's what's shown here. We have a little stripy material made of A and B conveniently arranged into little columns. And we're going to make this box, which the idea is that the box used to be this big, and then it's gotten shorter so that it's where the colors are fully have their full intensity. So these little sort of grayed out, not grayed out, but purpled out lavender parts of the box are the strain. So we loaded this whole thing and it got shorter. But in this diagram, you can see that B is meant to be stiffer. So you have to push harder on the columns of B to get them to get shorter, the same amount. So the strain is the same, but the stress is not. So we can calculate a Young's modulus for A and B. And we can say, well, the strain is all the same, and I'm not going to go through this math, but you can do a bunch of math. And in the end, you can get the ET, which is the total Young's modulus for the whole thing. And it depends on the area that you have dedicated to A and to B. And they just kind of get added together like that. Okay, so that's the Voigt isostrain assumption. In contrast, we have the Royce isostress assumption. So this says, okay, well, the stress on all of the material is the same as the total stress, but the strain is going to be different. So in this illustration, we have conveniently rearranged the material so that the squishier material, which is A, is in horizontal bars. Okay, so you have the same load across the top, but the amount of deformation in A and B is dependent upon the Young's modulus of A versus B. Okay, so once again, I'm not going to go through the math. I just have it there so you can say, yes, it exists. But we basically at the bottom come up with a formulation for the strain here as a function, that the overall strain, total strain, is a function of the strain in A and B. And then we continue on to calculate from that the Young's modulus for the total. Okay, so that's the Royce isostress assumption. Now, what people did is they started thinking about, okay, what does this mean? So here's an example of how material with different amounts of phase A and phase B would behave. So on this axis, I have the modulus of the two phases, and on this axis down here, I have the proportion of material A. So down here is 100% material A, and you can see it's got a modulus of 1. And over here, I have 0% A, which means it's B, is 100% B, and it's got a modulus of 10. So we have these two very different materials, and this is an extreme example, right? That doesn't happen very much, but it sort of illustrates what's going on. So if you look at the way the the moduli are formulated for the Royce and the Voigt assumptions, you see that you get quite different answers as a function of what the mixture of the material is, right? So this line up here is the Voigt assumption, and this is the Royce assumption. So fortunately, we don't often have materials that have such divergent elastic moduli, but you can see, kind of here in the middle, we really don't have a good idea because these are two assumptions. And how would you know which is the right assumption? So we basically know that both assumptions are wrong, right? That when we formulated these assumptions, not me, people formulated these assumptions, they knew they were both wrong. But it's kind of like the spherical cow problem. You have some really complicated thing and you make a first gloss approximation. So they said, well, both are wrong, but we have this kind of envelope. So let's just take the average and that'll be better. So they have the Voigt-Royce-Hill average is this red line in here, kind of comes through the center. Now that looks actually kind of seems to work pretty well for most folks, but it wasn't satisfying to physicists because physicists always want to pursue the truth. So physicists came up with another way to solve this problem, and it's called the self-consistent formulation. And it uses this notion that you could look at each crystal in the material. So over here, I have a little diagram of your material, and it's got little lines in it. You could think of them as slip planes or whatever. They're just to sort of give you an idea of the orientation in my little sketch. And you could say, well, this crystal has its set of elastic constants, and it has this outer boundary condition that's pushing on it, but we really don't know how it's interacting with everything else. And so we could consider that crystal as an inclusion inside of the matrix. And this problem of solving how a little elliptical inclusion, it could be a spherical inclusion. I've used a sort of non-specific inclusion as an ellipse, but anything as long as it's elliptical, Eshelby's theory can solve it. So basically, you say, I have this spherical inclusion. It has its elastic constants. It's sitting inside a homogeneous elastic medium that's made up of everything else in the material. And then you can solve the boundaries for this ellipse using Eshelby's theory of inclusions. And this is back when people didn't have computers, so they were really interested in closed form analyses that you could sort of write down on a piece of paper. Okay, so the way this works is you have to iterate essentially. So you take your model and you have a large number of crystals, each with its own orientation, and each one has its own single crystal elastic constant. And then the model basically takes the first crystal and it says, okay, I am going to deform it inside of the elastic medium, but I have no idea what the elastic medium is doing. So I don't know, I just sort of make some random guess. And then it goes down and it grabs the next crystal and it says, okay, well, I'm going to solve this problem. I still don't know what the elastic medium is doing, but I found the last crystal I did, so I'm going to use that for the elastic medium, right? So it keeps on going. It runs through the whole list of crystals. And then by the time it's run through the whole list of crystals, now you can average together the answer for the stress and the strain in all of the crystals to make your homogeneous elastic medium. So now you say, okay, now let's go back to the top of the list of crystals and we start again. But this time we have some opinion about the homogeneous elastic medium and what it's doing. So you take your first crystal and you put it in the homogeneous elastic medium and you use Eshelby's equations and you solve the stress and strain for the inclusion. And it's like really different than the first time because you didn't know anything the first time. But so you say, okay, well, that's better. And so you run through the list of crystals again, and you keep running through the list of crystals and solving these equations until nothing changes anymore. And that's why they call these models self-consistent. So it's kind of a bootstrap thing, right? It's kind of like, I don't know anything, but we'll just make up shit. And eventually, after you've iterated enough times with any luck, you've iterated to a, a solution for every crystal in the material that is consistent with all the rest of the crystals in material. And so the way these models work is you do a single tiny increment, you get a self-consistent answer for the first increment of your problem, and then you go to the next increment. And it just sort of walks along like that. So it's iterative, and the model will converge on your answer. And this technique was, developed by physicists, and it's used a lot by metallurgists. And the way I found out about this was when we first started doing synchrotron diffraction, and we realized, oh, this is not quite what we thought. I just sort of dove into the literature and I found out that people doing metal deformation in with neutron diffraction had already stumbled into some of the problems that we were encountering. And this is what their solution was. So going back to the comparison between the Royce and the Voigt and the self-consistent average and the Royce-Voigt-Hill average, here we have our Voigt solution and then the Royce solution, and then here's that average between the two, and you can see the self-consistent kind of splits the difference, and winding up more or less in the same place at 50-50. But if you have huge differences in the compliances of various things in your material, then there are differences in the answers that you get for different percentages of the material. Okay, so one place that you can do these kinds of calculations is this website from MPIE, which is, I always forget where they are called, but they're a very, very useful university somewhere in Europe, Germany. So anyway, this is a self-consistent calculation. And so let's say you have single crystal constants, which remember our single crystals are anisotropic. So instead of thinking about material A and material B, you can think about olivine in one orientation and olivine versus in another orientation. Okay, so let's say you have a set of CIJs that you like, and now you're like, well, what is the bulk modulus for this material? And so you can get that from the SCEMA website. It's got a little application. You just plug in your numbers and it will spit out a little pretty picture of your CIJs as a function of orientation. And it will give you the bulk modulus by the self-consistent method, the Royce method, and the Voigt method, and the shear modulus. And you can see, and the Young's modulus and the Poisson's ratio, you can always calculate those um, for the Royce and the Voigt from the other equations we had. So anyway, the major point here is that if, as you're working along, you're busy calculating your CIJs as a function of pressure and temperature, you don't necessarily have a bulk modulus that goes along with that. So this is a handy way to get a hold of your bulk modulus if you happen to need it. Okay, so this works for cubic through orthorhombic. Unfortunately, they don't have monoclinic and triclinic, but hopefully you're not working an awful lot with monoclinic and triclinic materials because they're miserable for lots of reasons. Okay, so you might have a question, where do I get these single crystal elastic constants? And basically you get them from the literature, but we always start with this book, which is probably, I don't know, it's 1995, which you're thinking, oh, that's from the dim and misty past. But for people like me and Yan Bin, this is just yesterday, right, Yan Bin?
Right.
So anyway, so this is AGU shelf reference, and it's super handy. And there's some really good articles. There's one by Yingwei Fei on thermal expansion. And then there's Jay Bass's Compendium of Elasticity of Minerals, Glasses, and Melts. And the minerals is very useful. And then the elastic constants of metal minerals at high temperature and pressure also is handy. So this is just a great reference. And often I find that there isn't a whole lot new since this paper was written when we're working with a new material. But the thing is that even if there is new stuff, they're going to reference, if not the handbook, they'll reference where their handbook got its constants from, right? And then so you can sort of do the search forward in the literature to find who in the recent past has been citing these elastic constants. So that's a pretty good way to kind of get in there into the literature. Okay, so now I'm going to spend a little time having reminded you of elasticity and how complicated it is. I'm going to talk about synchrotron diffraction for a little bit. Okay, so this is a sample sitting in the synchrotron beam. And out here, I have got the energy dispersive array of detectors. So I do all my work with energy dispersive, the 6B and B setup. And in this particular diagram, I have not put in all of the other detectors. I'm just focusing on the top and bottom detector, which are hopefully are still called 1 and 9, and the side detectors, which are 5 and 10. A lot of times I'll refer to these 5 and 10 as the transverse, and these guys are sort of the compressive direction detectors or something. But this is an important point I want to make. So we have a whole bunch of crystals in the material. We're shining an X-ray beam through it, and all the little crystals or crystallites, whatever you want to call them, they're all participating in diffraction, or at least some subset of them are participating in diffraction. And we use Bragg's law, which is n lambda equals 2d sine theta, except um, this is the sort of sine theta's constant for monochromatic, and it's not for energy dispersive. But anyway, we don't need to worry about that. But basically, you can get from from the angles. What did I say? Oh, it's mono. I'm pointing the wrong thing. Okay, so 2 theta is the thing that's constant in energy dispersive, and it's the wavelength which is changing. Whereas if you're doing monochromatic, the 2 theta, you measure a bunch of different 2 thetas and you have a single wavelength. Sorry, got that inside out. Okay, so going back to what's happening, we have the X-ray beam coming in and it's diffracting off of a bunch of different grains. And so I'm showing grains with sort of different orientations, and they're contributing to the diffraction peaks that you see in each detector. And the point I want to make is that each peak in each detector is coming from a different group of grains. So this peak in my little energy cartoon of an energy dispersive diffraction pattern, This first peak is not coming from the same grains that contribute to the second peak because they're in different orientations. They're diffracting into different orientations. Um, and it's also not the same, this different group of crystals in the third peak, etc. And furthermore, the crystals that are diffracting into this peak are not the same group of crystals that are diffracting into this peak down in the transverse detectors. So I like to think of the diffraction patterns. We tend to think of, oh, it's the material, it's all one thing, but it's not. It's like the population of the United States. We have people who live on the street, and then we have Jeff Bezos, and and then we have everything in between. So the crystal has a very diverse population, and each peak is only giving us like a little choir of some subset of the crystals in the material. And so each little subset is going to tell you a slightly different story. So that's important to remember as we go forward. So I had some little diagrams here just to make the point, because usually I like to wave my hands, but I'm not there to effectively, yeah, do this stuff. So anyway, so the idea is when you have the stress coming, I'm showing it being vertically oriented, and here are my little lattice planes. When you're compressing normal to the lattice planes get shorter. That's kind of what that was supposed to do. Okay. So if we look at a peak, like a given peak with, in different detectors, that's what I'm plotting here. So here's D-spacing, here's the intensity, and I've color coded it so that the orange and the pink are from the transverse detectors, 5 and 10, and then the blue guys are from detector 1 and detector 9. All right. So what we see as we deform the material is the D-spacing for lattice planes that are basically perpendicular compression gets shorter. So they move out here. And for the transverse detector, they actually get longer. They move off to longer D-spacings. And that's kind of the Poisson's ratio effect, right? So if you have up here, I've got the little diagram for monochromatic, and you can sort of make the same diagram by pulling out the D-spacings for all the different detectors with the 10 detector system. But basically what we see is that the D-spacings, yes, I'm looking at my screen, it's chopped off at the top, but you guys, whoops, no. Okay, you see the whole thing. So the D-spacings get shorter. The blue is kind of the after, and the little dashed lines are the starting point. So these are little Debye rings. So basically your circular rings turn into an ellipse, okay? All right, and now the next thing, going back to different groups of crystals in different peaks telling you different things, it's important to keep in mind how that kind of pans out with regard to the orientation of your detectors. So if we think about crystals that are diffracting into detectors 1 and 9, where they're perpendicular to compression, even though we have a bunch of different crystals, they all have they have some things in common. So that's what I'm trying to illustrate here. So imagine that here's the diffracting plane for all the grains that are diffracting into the detectors 1 and 9. And the fact that they're diffracting constrains it, that's how it chooses which group gets to be here, right? That they have their diffracting plane like that. But it doesn't constrain them in as to which grains get picked in perpendicular to the compression direction. And this is so hard to do without my hands. But basically, a grain can be diffracting into this detector independent of whether its slip plane is oriented here or whether it's oriented here. So the idea, I've got this little cone. Can you all see the cone? And what I'm trying to show is that you have slip planes in a bunch of different orientations. So you have crystals with different orientations. They share the diffracting plane in common, but the position of the slip plane is not constrained by the fact that they're diffracting. Does everybody get that? Let me see. I can't see you all. Are you totally lost? Do I need to explain more? No? Okay, Matt's got his thumb up. Okay, I'll go on. So one of the things that this group of crystals then has in common, in addition to the diffracting plane, is their Schmidt factor. And I've got a little diagram over here showing how we calculate the Schmidt factor, but it's basically the amount of shear stress resolved onto the slip plane. So all these guys have the same Schmidt factor. So if we looked at the resolved shear stress on the slip direction, as a function of this little phi angle of how they're all the same, okay? Now, that's a lot of thinking for something that might not be important, but it becomes important when we think about what's going on in all the other detectors. So for example, I've illustrated the transverse detectors. So in the group of grains that are participating in a diffraction peak in the transverse detector, they all have this diffracting plane here. And similarly to the group I discussed at the top, they 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 are not constrained as you swivel around in a pole to that plane. So that's what I'm showing here. This little cone is showing all of the grains can have slip planes that kind of participate in this little cone. Now, the difference is if you look at the resolved shear stress on the slip direction as a function of this angle going around that way, it goes like this, right? So you have a group of grains that they are diffracting together, but in terms of deformation, they're doing all kinds of stuff, totally different stuff. And so the averaging that goes into the transverse detectors and all the other detectors around the circle is different than it is for this group of grains that diffract into the detectors where the diffracting plane is perpendicular to the normal stress. So that's really important. And in my mind, it kind of explains why a lot of times the diffraction, for us at least in the energy dispersive situation, the diffraction from the compression detectors, the ones that have the diffracting plane perpendicular compression, that's cleaner. It looks much better than the stuff on the sides. And it's because you have these bizarre kind of averages going on. Okay, so the key takeaway is that, oh, and I should have said this is also true of the elastic tensor. So you imagine those little elastic tensor shapes. They have the same kind of thing is going on. So the grain populations diffracting into detectors 1 and 9, they share the same elastic properties and the same plastic behavior. Whereas the grain populations diffracting into all the other detectors are mixtures of grains with different elastic properties and different plastic behavior. So that's an important thing to keep in mind. Okay, so now I know I'm kind of jumping all around here, but there's so much to talk about. So I wanted to talk briefly about things that we've learned over the years about how to collect data that's useful. And this comes from having spent a lot of time collecting less than useful data. You go to the synchrotron and you work really hard and you come home and you go, ah, okay. So there, you may have heard some of these things, and seeing as I'm parachuting into your workshop, I have no idea what you've heard before. So anyway, I'll just go through some of these really quick. You want to choose a sample that has a small grain size. And if you don't, then you are going to have to use the stress gauge, but you need something in your cell that's going to diffract really well. I found that fully dense sample materials are good. We started out by having like little cylinders and packing powders into them. And you can work that way, but you get much better data if you have a rock that you can core, and then you have a little cylinder that you drop into your sample assembly. Um, Now, once you have a, a little core that is not going to compress very much because it's not full of holes, then you have to think about your crushable alumina, which is going to be in the cell above and below your sample. You have to make sure you have enough because what you don't want to do is get to your where you're going to deform your sample and you've already busted it, right? You want your sample to maintain its kind of right cylinder geometry um, to the point that you're ready to deform it. And you also don't want to have a sample that's at 9 GPa differential stress because it's going to be almost impossible to get rid of that stress in order to do an experiment. Another thing, yeah?
Yeah. It's people outside. Yeah. Oh, wait, sorry.
Oh, okay. All right. Sorry. So another thing that we learned kind of the hard way is that we need to take control of our JCPDS files, right? So the Beamline will have like an infinite variety of JCPDS files for you to choose from, but you don't actually know whether the previous user has gone in and modified things, right? So so it's always good to just have JCPDS files that you know are correct and have the correct despacings and the correct moduli in them because they will have the bulk modulus, usually like the bulk modulus and the pressure derivative of the bulk modulus. And you want to have the JCPDS files for all of the things in your cell, right? So, the alumina and nickel, at least in the diffracting part of your cell. We use a nickel foil. So if you have another material like platinum that you're using for the bottom and top markers, then you want to have diffraction for that as well. You want to have your JCPDS for that. And of course, it should have the right bulk modulus. And then another thing that we've learned
Yeah.
is,
Sorry, does everybody know what a JCPDS file is?
oh,
Yeah.
that's
No. Okay, I don't think they all know what it is.
okay.
It
All
gives
right.
you the diffraction, like the despacing of the mineral in question, but you
Yeah.
can explain it if you want.
Okay. Yeah. So actually, where do I have? I have a JCPS file here. I wonder if I just
I
double
think
click on it. Aha.
I,
Yes.
okay.
Okay.
Yeah.
Yeah.
Good enough.
So
Yeah.
this is a JCPDS file for Lumina. And I was going to talk about this later, but I can put it in here. So basically, when you're on the beamline, have you've been to the beamline, right? A little bit?
Yes.
Yeah.
Okay.
Yeah.
So you have diffraction, your diffraction peaks um in the oh, I always forget what it's called. I forgot it the other day, Matt.
MCA.
Huh?
MCA.
MCA, thank you. Yeah, you have your diffraction peaks in the MCA and you want to compare them. Like, what are those peaks? That's when you pull up your JCPDS. And so um, there's some just information at the top, the bulk modulus, the pressure derivative of the bulk modulus, the symmetry, and then the A and the C, which is for this particular alumina, which is hexagonal. Those are the two independent cell parameters. And then you have this is the thermal expansion, alpha T. And then you have these columns, and each one says DIHKL, which seems to be sort of like something telling the program what to expect. So the first column here is the despacing of your material, and these guys should match your source, your believed source, right? Where for the like if we're working with new material, we'll go to the MSA crystallographic structure database and get those, right? So, and then these are for diffraction. So, the next column is the intensity of those peaks, right? So for those of us who are really old, this is how you used to identify things and XRD, right? As you ran a pattern, then you could look at the despacings and see what the intensity of the peaks are. So 45 means that this is like half as intense as the 100% peak, etc. And then over here, the last three columns are HKL. So these are your Miller indices for the planes in here. Okay, so that is what the JCPDS is for. And the reason you want to know that it's correct and nobody's gone in and edited stuff, because obviously if you pull up this data file and the MCA, and somebody has changed this number on you, the peak won't be in the right place. All right. Okay, so I'm going to figure out where I was. Go back here. Okay, I think I was here, right? Yes, because I was talking about the JCPS files. Okay, so the last thing I wanted to say is it's important to not to ask too much of your sample, because there's a point, you've spent a lot of time making your cell and getting it onto the synchrotron and centering it and pressurizing it. So you want to get as much data out as you can. But on the other hand, if your cell goes to pot, you judges will just take it out and start with another sample and what remaining beam time you have. So I don't know how many times we've come back home and said, oh, the last half day, we probably shouldn't have bothered because our sample was just too sad. So basically, when you do long experiments with high strain, the geometry of the sample deteriorates. And so sometimes your diffraction gets kind of wonky. It's not quite the shape you thought it was anymore. High temperature experiments will start to affect the grain size. So if you have larger grains, then you don't have a good statistic, you don't have statistically significant populations of the things that make up each diffraction peak. So sometimes diffraction peaks get really big and they get really small, and it gets very hard to figure out what you're looking at. And another thing we've had problems with is if you're sitting at high temperatures for long enough, you can actually kind of diffuse the foils away. They just sort of fade out. And they're still there when you go and cut the sample open, but the metal starts to move into grain boundaries and it gets really hard to figure out the length of your sample. Okay. Other things that we've learned, if possible, use a calibrated cell. Hopefully the beamline has got a calibration for you. Because thermocouples, they're miserable. It's a problem that the community has not really solved. So sometimes you get good data from a thermocouple and sometimes you don't. It's good to plan to do a doable experiment. So the lattice parameters that you measure, they're a function of temperature, pressure, and stress. So at some point you run into non-uniqueness. You have a d-spacing of 5 or 3.5. Let's say that'd be more realistic. But you don't know what it means because you don't know what the temperature, pressure, and stress state is. And you can no longer solve for anything if you don't have enough d-spacings and you've wandered off too far in pressure, temperature, stress space. So we always just sort of change one thing at a time and then take some diffraction to keep from getting lost, basically. And it's important to remember that changing temperature will change pressure. So the cells have kind of their own equation of state, so to speak. So if you change the temperature, then you will get thermal pressure, etc. And we've found, and I think it's cell dependent, but we've used a lot of the sort of ceramic cells where we have the sphere and seats is, I think, the thing we've had the most experience with. And we don't really have good luck dropping pressure. So I find that if I want to do something at a bunch of different pressures, it's better to have a bunch of different cells. And it may be easier with the boron epoxy cells, but it's just a thing to keep in mind that at your high pressure and you try to decompress, sometimes you're pulling the anvils back and nothing's happening. And then all of a sudden you're back at zero because you have this big hysteresis. And also you can go up to pressure and you heat and then the cell gets mushy and it's really hard to continue pressurizing. So anyway, those are things that beamline scientists can help you with. What we found is that to sort of keep it simple and sweet and not try to do too many different things with the cell once it's in is better. We like to take a sample image before we put the side anvils in so that we know what our sample actually looks like. So before the anvils go in, you actually can see the edges and you kind of have some clue of where you are. Because once you put the anvils in, then you just have this little slit and you have a few dark lines. And sometimes, especially if you've got a piston at the top and a piston at the bottom or whatever, you can kind of get yourself lost. Um, I don't know if the empty cell scheme is so useful anymore, but because we've done experiments over roughly 20 years, and so things have kind of changed over time. But we used to get more diffraction from our cell that would get in the way of the sample. So we would come in with an identical cell that didn't have a sample in it, so we call it the empty cell. And we would take a spectra of that before we started, and then we would subtract those spectra from all our diffraction. Which was very helpful. And another situation is if you have high counts, with the energy dispersive detector, you can have something Matt refers to as pileup. And we had a lot of experience with things piling up and concluded that basically if you have a lot of counts, the peaks can start shifting channel. So we always use the same collection time for the standard and the sample. So now you're saying, well, you to collect your standard for 20 minutes. Well, we would just take 21-minute spectra and then add them all together and analyze them. Okay, so when we do deformation, it's like really important to start from a hydrostatic condition. And there's this thing called residual stress, which can be really problematic. Like already, if your sample already has a whole bunch of different stress states in it, it gets much harder to figure out what your imposition of a boundary condition did to the sample. So it's always good to anneal because once you pressurize, if you cold compress, you wind up with stresses in your sample. It's almost impossible to avoid. So you need to relax those residual stresses by annealing. And then often if we anneal at high temperature, you want to go up to, sort of 75% of the melting temperature or something like that. Um, Once you drop the temperature back into the range of temperatures going to use, the cell often puts the sample into a slightly tensile situation. And it's not really tensile because you're still all high pressure. But anyway, a slightly tensile state is a good place to start a deformation experiment from. So we've done a lot of things that have involved, we use fully dense samples. So that means they don't change length very much when you pressurize them, and you wind up being in a state of very high non-hydrostatic stress. So like I said, you don't want to break your sample before you even start. So we've done things like you leave a little space above the sample, like we take the top the crushable alumina, and we just like dig a little divot into the center just to give a little extra space. We've also done things like shortening the cube slightly. So now the cube is no longer the same height as it is wide. And then there's this, we would run the D diagrams either during compression or we'd run them in a little bit during while we're actually closing the cell up so that we have some ability to back the rams off once we get to our high pressure, high temperature condition, or the high pressure condition rather. And then using a slightly shorter sample is a good way to do it. We've had good luck with all of those strategies.
Okay,
Yeah.
Pam, I add another strategy a group of you are doing is they shimming the side angles at
Okay.
shimmings. So the
Yeah.
equivalent to your shorten your sample. It's
Yep.
equivalent. Yeah.
Yep. That's another way to do it.
Yeah, you can add that strategy too.
Yeah. Yeah. There are lots of
we
strategies.
often do is we actually make the vertical height of the cube shorter on
Yeah.
purpose.
Yeah, that's what
We have 7 millimeter cube, we make the height 6. And then we move the differential ramps ahead of time by about 1 millimeter.
shimming strategies.
Yeah, the shimming
Yep.
does the opposite though, because it pushes the sides in, so it relatively
Yeah.
makes the cube longer.
Longer.
in
Yeah,
that
yeah, yeah.
dimension. Yeah.
Yeah, it's kind of like a slight tensor.
Mhm.
Yeah.
So there are many strategies.
Right. Yeah, there are. But the important thing is that this is something you need to think about, right? Okay, so we found early on, I think taking pictures were more painful in the beginning. We never took enough pictures. Just like when you have a baby, it's like, oh, I don't have enough pictures. So you want to take a lot of pictures. Pictures are cheap. So to keep track of your sample. Um, we scan during diffraction. We use the dispute program to maximize the diffraction volume because the statistics of having enough grains to get really good diffraction is super important. And so if you can run up and down while you're collecting your data, that's good. And so you have to note the position in Z and sort of figure out where you're scanning to and from, and that's all so that you can enter information into this dispute program. But one thing to be aware of is this idea of shadowing. And I was, if I had extra time, I would have drawn the little picture. When we're on the beamline, we're always drawing pictures of how the diffraction works. But basically, if you have something that's creating a shadow, like a metal foil, and you get too close to that, you're going to start cutting off some of the X-rays that are getting into the detector, and you cut off um, cut them off in such a way as to shift the peak from side to side, right? So we found that you want to be the center of your beam has to be like at least another 100, the top of the little box where your beam is, right, has to be another 100 microns away from the thing that's creating a shadow to get out of the situation where the metal foils are changing your despacings. So we always, we use dispute and we take diffraction from the sample and our pistons, or if you have a stress gauge, back and forth. So we try to get as much information about what is going on as in the cell as possible. And we alternate the images and diffraction. When we do ultrasonic, we put that in the mix. So because you cannot take your images at the same time you take your diffraction. So what you're going to wind up doing is building a time series for your sample length in which to pick out the sample length at the point at which you're actually collecting diffraction, because you want to put together a stress strain curve and you want them to be time synchronized. So you always want to be going back and forth between the imaging and diffraction so you're not projecting too much. It's not too much of an interpolation. And the other last point that causes various pains at various times is the computers may or may not be synchronized with each computer you're looking at has its clock. And the crate has a clock, I assume, still. And
We don't have crate anymore.
you don't have the crate anymore. Okay.
Yeah.
So this may be out of date, but basically, because there are multiple computers, if you are saving your diffraction data on one computer and your picture data on another computer, the computers have to have the same time on them. And if they don't, you're in trouble. So this may be because the crate's gone, maybe that's not a problem. But basically, you want to check ahead of time, make sure that you have a common time frame for all of the devices that you're using. All right, so now I want to talk briefly about sample strain and how we do that, because my understanding was that Caleb wasn't going to talk about sample strain. So, you've got image day on the computers there, so here's a picture of like one of our samples with the foils, and we're going to measure our sample between this lower foil and up here, and this is probably one of our alumina pistons. So you just sort of drop a line in there with image J and you say, okay, I'm going to pick this fuzzy edge and I'm going to pick this fuzzy edge. So that's easy enough. But when you get home, you want to spend a little time doing this. And everybody has a slightly different way of doing it. So I thought I would talk just briefly about what we do, because it's fairly simple, is that we have a little program that we can share that basically plots the standard deviation along the rows here for the entire image. And the reason we went with this is because that way, we come home, we get 1,000 images. So, we take lots of pictures. So it's hard to go and measure each one by hand. And so we just wanted something that we could say, have a program pull a profile out of this picture. And the easiest way to do this without having to hunt where in the center is to just take the standard deviation. So if you look at this row here and you're calculating the standard deviation of the image in this pixel, the pixels in this image along through the foil, you're going to have a very low standard deviation. Whereas if you're coming along through here, it's dark, 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 and then it's bright. It's very different. So you're going to have a high standard deviation. So what we do is we calculate the standard deviation along the image rows, and then we plot those as a function of image row down this way. And then we put the whole thing into Excel, and we use the first image. So this is one of these intensity profiles here. It's not an intensity profile, it's a standard deviation profile. We have those for every image, and we can compare them to each other. And therefore get the sample strength. So it's kind of like a image correlation with like a hammer, I would say, this sort of brute force image correlation. So we stretch the first image in our sequence to overlay subsequent images. And then we take the stretching that we need to do to give us our strain. And you can also, if things change too much, you can do it image by image, or, like image 7 versus image 14 or whatever. So you can get out incremental strains. So like I said, this is like image correlation with a hammer. We just use Excel. We take the data. There's the rows here and the standard deviation, and then we have the ability to kind of shift it around in the image, and then we take the photo that we're interested in, and then we do basically Y scaling and Y scaling and X scaling until we get them to match. So you can see here's a little profile overlay. And so then we have little windows that we can zoom in. So here are two images that are, these are probably hours apart because it's 18 versus 35. And you can see that the profiles actually are very constant over time, which is very useful. So then you can stretch the original profile to get the subsequent profile, and the little dashes, it all kind of lines up. We don't use a calculation because it's like how matched is it? Because your eyes just basically allow you to do this. So that's kind of handy, and we get very nice sample strain curves out of this. So so on here we have the sample strain from our image matching, and then we have, I think on this axis, this should be time, but it looks like it's accidentally not time. It should be time. Anyway, so we have a time sample strain, and you can see the little curve it's very nice. It fits well. And then we just use a polynomial to calculate what it should be. And initially we started using a line. So I just wanted to, I dropped a line on here so you could see for us, especially early in our deformation sequences, because we do multiple sequences of deformation, the machine is squishy. And I don't fully understand this, but basically we're running the D diagrams at a constant rate, but there's something that's kind of allowing the machine and the sample assembly to get stiffer over time. So the displacement over time is not constant, even though the motor speed is constant. So since we want to know the sample length at the time we're taking diffraction, right? We're using this equation to give us the sample length at the time of diffraction, and using a simple linear extrapolation it doesn't work very well. Often when we quote our stress strain rates, we'll take and fit a line to the latter half of the sort of curve, because eventually they do kind of straighten up and fly right, but there's always this sort of mushy part in the beginning. Okay, so how long have I been talking? Do people need to like stretch their legs?
You want to take a 5-minute break, or you want to continue? It's up to you guys.
Yeah, we're sort of like halfway through.
Yeah, what?
Yeah, it's a great idea. 5-minute break is great.
Okay, yeah, let's take a
Okay.
5-minute break.
Take some water too.
Yeah. Everybody gets a break.
Okay, 5 minutes break, stretch.
4 minutes and 40 seconds left. 6 minutes.
Yeah, give him a chance to. Still a few bottle cans of soda over there.
Okay.
So Pam is very super careful experimenter list. So you can see everything's very careful about and processed.
I'm super careful because I've had too many beam times when I came home and were like, ah, this isn't good.
Will you come back in the future?
Oh, maybe we'll see. We'll see. I mean,
We got a
right
new
now,
pedestal.
what?
We got a new pedestal. The old table is gone. The
Oh,
one
okay.
under the press, yeah.
Uh-huh.
It doesn't wiggle back and forth when you move it up and down anymore.
Still move.
Oh, how
Not too
nice.
bad.
Yeah.
Better than used to be. Because right now we have
Nice.
3 vertical motors to move the press now.
Uh-huh. And
Yeah.
what do you have instead of the crate? Just another
Crate
crate?
has been gone for 2 years now.
Yeah, the
2 years now, yeah.
crate isn't necessary anymore
Yeah.
because we don't run the motor controllers through that. Everything is run through Galil Electronics
Yeah.
that Mark
Ah.
distributed.
Yeah.
So we don't
Okay.
need the crate as a universalizer anymore.
Mm. Okay.
The main thing that really needed the crate actually was the ultrasonics, but that we replaced the interface to that as well.
Mm-hmm.
So
Okay.
everything runs without it. And as far as like time stamping the data files, since everything is saved to the same place, the timestamp on the file when it is written will be correct and in the correct order.
Okay.
And the worst case scenario is if the computer that you're running Epic's logger or dispute on is a second or two offset from the data server. But it's universal. It's not like it used to be where you could end up with 4 different time series and you have to figure out when they overlap. It's
Right. Yeah.
it's a universal stagger now, thankfully. So it's onward and upward.
Well, good. Good, good. Okay, well, I'm gonna take a break too. I'll be right back.
All right.
Hasn't been back since, no, how long she came back?
Oh, yeah, she was back. Yeah.
Yeah, maybe 2 years.
Because we were there with
Oh,
Karen and
upgrade.
Denali.
Since upgrade, she
Yeah.
hasn't come back. Yeah.
Yeah.
Okay, I guess you guys can think about what you did today at our Beamline is washing off, right? She's with us for 30 years, maybe more. Yeah.
Yeah.
She started in the 1990s also.
Yeah.
Yeah. So she's very, very advanced user.
In my opinion, one of the best teachers, like pure teachers that I've come across. So I'm hoping that you guys are getting good stuff out of this.
She's right now at University of Nevada, Las Vegas. So there are many high-pressure people are related to Stony Brook University. The Stony Brook University kind of developed the first synchrotron-based high-pressure research program, right?
Yep.
Yeah. So especially the deformation. So many people are from there, like Yan Bin. His PhD there, right? PhD postdoc also.
I'm not sure about postdoc, but definitely PhD.
Yeah, from Stony Brook, and Cam was a postdoc there, right?
Yeah, but with so there used to be an organization called Shipper, and Stony Brook was the head of that. She was at one of the other universities that was Shipper.
Yeah.
So she spent a lot of time at Stony.
Yeah, Tony, another Beamer science here. His Stony Brook graduate student.
Tony and I were graduate students together at Stony.
Yeah.
So we graduated like 6 months apart. His wife Natalie as well, also. we were all together. She and I were in the same class. Tony was the year before me. Now we were together.
Yeah, they produce many large volume, I think large volume research, right? Now number two,
Yeah, less so. No.
less so. Yeah. So basically, many people, high pressure people associate with Stony Brook University one way or other. If you go to Europe, to the meetings, many people know I made 5. No price you saw. So that's the first one in this country.
Pretty big stick in the. Filming around.
Where is the one stick?
The stick right now is with a student. With Grace, like Grace took it away. So you haven't got it yet?
Didn't get to the table.
Okay,
It just
I
went around
can,
the outside.
I can go over who else haven't have it. I go get from Chris because I can
Okay.
let you. Okay, I go get it. I know where Chris is right now. So okay, I go get the stick. That's you. Okay.
So for the people who have experienced the stick so far, there is a folder inside the Plot85 folder that says install files. There are 2 things that you're going to want to install. One is the Python XY that's in there. The other one is IDL. So those are the only 2 things that you just want to install. They take time because they're big, but you just double click it and let it run. That way you'll have them pre-installed when Caleb starts to work as
You
well.
don't need an IDL, right? You only need a virtual machine.
Right, so the installer installs the virtual
That's the
machine.
whole package.
Does
And this
anybody
particular
need
flavor of
permit?
IDL is the one Caleb uses, so he knows it's gonna work.
But how do you, oh, okay, you basically, you don't need a license to run IDL.
Right.
Yeah, that's right.
What I'm curious about is like if we use the latest version of the virtual machine, it may not run the program. You had where we upgraded from IDL 8 to 9, where a lot of our save files for the controls didn't work anymore. So it's like we know that the polydeptics and stuff like that will work on the old virtual machine from 8.5. So that's what he's got the install file for.
Yeah. IDL is going to be obsolete. Yes.
It's fifth ownership company in the last couple of years. I mean,
Oh, really?
yeah, it's getting sold to different companies. and
Coaching.
stuff.
Yeah, so I was kind of thinking about it.
So about the
Maybe I
electric,
can find
the
out, but I just come with
string
idea.
of the crushing
If
volume,
that has value, I might really.
to the string of
it
the
might
sample.
hold that even.
Because if the sample is training 10%, and the volume is 10% of the sample. Explain your solutions.
There's a lot of factors that can go to it. You have this column that has different compliances. And also, the oil compressibility changes dramatically with pressure. And you're driving hydraulic oil to conform it.
Idea.
So, although you're reading the oil pressure, it may not translate into
We can make some.
displacement.
The other part that's like a very unsatisfying thing, but we can't control it. If you're at high temperature in there, the temperature of the room changes, which changes the properties of the oil.
Yeah.
So the longer that you heat up, it will change your flow rate is going to be affected when you're trying to deform the sample. So there are so many variables that are really difficult to control some of that initial squishiness versus what you get later. There's a lot of it. It's not just the cells, what's inside the press, it's actually the entire apparatus.
And the cell itself also, as you compress, start forming the gasket. You compress more, there's more gasket. Until finally at some point, there's enough friction.
I don't know.
The gasket doesn't increase anymore.
Like
But there's some
supported by the US Army.
How much the temperature of the ring?
The
changes.
most thing.
It depends in part on the size of the cell and what the temperature is that you're going to. Also the cell materials, because like if you use yeah, and if you use MgO, MgO is the worst thermal insulator ever. So if you're pouring it out and pouring it, it's just flowing. So everything tends to heat up more, but if you use a more insulated exterior.
So if I should say,
or something like that,
anything cold?
it's much
We
more,
want to do that, but we
the
haven't done
effect to the
yet.
room is much less.
But there's a couple things you can do. You can put a furnace in it, like we normally do with our regular experiments. So then you cool it down to whatever temperature it cools down to, and heat it up to whatever temperature you want to go to your furnace.
Yeah.
That's one way. The other way is just control the flow of liquid nitrogen. And that will impact the temperature. I don't know how accurate that's gonna be. I have a feeling like it'll start cooling down, so that if you want to higher, you slow the flow rate, but you overshoot. I don't know. Maybe that works well.
It's done.
Yeah, she just.
Right. I think now
Yeah,
we've had
it seems to
11
me
minute,
like
5 minute break.
Yeah.
Okay,
I think
Are you all back?
yeah, let's go back.
I think in the
But there's
majority of
some
communities, yes.
aspects of that.
Okay. So ready to start?
Yes, please.
Okay. All right. So, yeah. Yes. So I wanted to talk just briefly about working with MED files, because they're really handy to know how to pull them apart and do things with them on your own. So the MED files are the ones that the MCA produces. They are your diffraction data. They have ASCII format. The data structure is therefore very simple. And you can extract the spectra and do all kinds of things with it on your own. I have a lot of little Fortran codes, but it's Fortran, so it's easy enough to write in R code or Python code, whatever. So this is what an MED file looks like. It's got a really big header, and the headers sort of change depending on how you set your run up. I think I circled the timestamp because that was so important in the past. But basically, you have a bunch of stuff at the top that tells you information about the status of the machine at the moment you're collecting the diffraction data. And then there's this little word here that says data, colon, and below that you have a string of numbers. And so these are your spectra by channel. They're listed. The channel number is not listed, but it's assumed. So the first row is 0 and then 1, 2, 3. Okay. So, and what's in the little boxes here are the intensity, right? So you actually can see the peaks by just looking at the MED file. Like here's our first little tiny peak. You can see, oh, we have some counts here. Okay, so because you can take it apart, you can do things like I mentioned, taking a blank cell and subtracting that spectra out from your spectra. You can do that. You can calculate your own d-spacings, and you can display your spectra in different ways. So this is just showing, again, sort of brute force. You can take the EDF parameters that you generate when you calibrate, and using the equation I've got the equation over here. You can use this EDF parameters and your 2 theta to give you the d spacing. So you can have the d spacings in your Excel sheet, and then you can plot your peaks. And you can also, we do a lot of these waterfall plots with our spectra. So we pull out each detector versus time. So on the x-axis here, that's the channel number, z is the intensity, and then the y on this plot is different spectra. So you can see your spectra over time. That gives you an idea of, like, do you have rogue peaks floating around? So like you can see we're doing really well on this peak. It develops 2 peaks, don't know why. But then we come back at the back, at the last spectra, we have this huge peak, right? So if you're running plot 85 and you're just analyzing peaks, you don't have a context necessarily. So having them in a waterfall plot so you can see what the peaks are doing, and if they are developing little shoulders or friends pop up, is very helpful. So we can do that. And then I had, yeah, this is the slide we did before about the JC PDS. And then I also had information about what the EDF file looks like. So when you're running plot 85 and you do the Illumina calibration, you get your EDF parameters there, also in an ASCII file that you can pull the numbers out of and do your own calculations for despacing. So I am not, I guess I made this, let's see. Yeah, this is just, I think Gabe, I want to say Gabe, but that's not his name. Caleb. Caleb is going to talk about loading the data and using plot LVP. So I'm not going to go through that. But just to show you that what your goal is with your first data analysis is going to be producing plots of despacing versus time. So this is a plot for one of our experiments where we do deformation sequences. And I'm just plotting 3 detectors and a single peak on those 3 detectors. So you can see as we compress, the despacing shrinks for detectors 1 and 9. It gets wider for detector 5. And then we do a deformation sequence. We stop, we anneal, and then we go back to roughly, sort of, this is not hydrostatic, but we're in tension. And then we deform again. And then we stop and we anneal and we deform again. And then I'm not sure what happened here, but here's another deformation sequence. And you see this last one, we did not get back to a hydrostatic condition ever. So you can see that detector 5 and detector 1 and 9, they don't meet. So we abandon that little sequence. But we are able to get typically 4 deformation sequences at different temperatures out of a single experiment. So now I want to talk about how you get stress out. So this is kind of more theory. And first, I'm going to talk very briefly about Singh's method, and then I'm going to talk about EPSC, even though I don't think you guys wanted me to talk about it. I think it's important to talk about, so I thought I'm going to talk about this. All right. So, and for all of these methods, you need your elastic moduli at pressure and temperature. So that's a little bit of science all by itself, is figuring out what are the elastic moduli and how do they change as a function of temperature and pressure. Okay, so the first way of measuring stress is basically using this sort of Reuter-Boyce strategy. Reuter-Boyce, sorry. And so this is from Singh's paper, and he points out that basically, he's talking about the stress tensor is equal to the mean stress versus plus the differential stress. And then he points out that you can get the despacings. This is his primary equation here, which is the DHKL, the mean DHKL is equal to the differential HKL is equal to and I think there should be an L here, but anyway, the sort of mean stress equivalent of the HKL, and then you have this equation here which includes this diffraction elastic constant. So the diffraction elastic constant is equal to the differential stress times this equation here, and he shows you how you get these. Well, this is the Q factor, rather. This is the diffraction elastic constant. And he has the equations for calculating using the single crystal elastic constants, these diffraction elastic constants. And so he has them for everything all the way down to triclinic, and you can see they're miserable, but people have programmed them, so you don't need to know about that. So there are problems with this analysis. And I would say the advantage, and this is why everybody uses it, is that it's been programmed up and it's pretty simple. The problem is that it gives you different answers for each peak. So, and this is one of the first things that we all discovered when we started working with this. with the D diet back in the early, 2005 or something like that, is that basically Singh's formulation assumes that you're somewhere between the Reut and the voice state. And it gives you different results for different lattice planes. So if we look here as this table from May et al., 2010, he has listed here his temperature, pressure, strain rate, strain for his experiments, and these are all on olivine. And then he gives the stress derived from 3 different lattice planes, the 130, the 131, and the 112. And the 130 typically gives the higher stress. So in this particular one, it's 4.2 GPA for the 130. The 131 gave him 4 GPA, or them, rather. This is Bill Durham's group. And the 112 gives 3.2 GPA. So you have a 30% difference, I think sometimes 40% difference between the stress you get from different lattice planes. So their solution was to take the average. And that is certainly kind of an acceptable way to do things. I'm showing here my first quartz data set. And we have the same thing. You see that the differential stress calculated from the lattice planes is, kind of similar when you're at very low stress in the elastic region. But the minute you get yielding and you move into plastic stress, you see them sort of pull apart from each other so that by the time we're at 8%, the 100 is giving us 1.2 GVA for the strength of the sample, whereas the 101 is giving us 0.8 GPA. So this is kind of the reason that the folks who developed the elastic plastic self-consistent technique decided to develop this technique, is because they saw the same thing with metals when they were deforming those in the neutron diffraction setup. So just to give you a preview, I'm going to talk about what how I got these, but this is an elastic plastic self-consistent model showing the differential stress for a group of lattice planes versus the macroscopic strain. And it gives you the same thing that we see in the synchrotron. Different lattice planes give you different stresses. All these guys are different lattice planes, but the model calculates the macroscopic stress. And so you can see for the group of lattice planes that I chose to model, the macroscopic stress is kind of in the middle, so maybe averaging them would be fine. However, if you only measured these guys down here, the average of this group is not going to give you the macroscopic stress that's actually in the sample. So what the EPSC does is it takes into account that sort of complexity. So back to this. So I talked about this idea before when we talked about elasticity. And so the elastic plastic self-consistent model, it yields a single macroscopic stress, which is consistent with everything you measured in diffraction. It takes all the grains in the sample into account, not just the ones that happen to be diffracting. And it allows you to see things you didn't think were happening. And I'll talk about the things we've learned by doing this from the diffraction. And you can also back out the critical resolved shear stress of slip systems if the system is cooperating with you, which is kind of remarkable because usually to get a single crystal, to get a critical resolved shear stress, you need to do a single crystal deformation experiment. Okay, so what the model looks like is it's a Fortran code. We use codes from Carlos Tomé at Los Alamos. And these guys are freely available, and I can share stuff I have. Sebastian Merkel has codes as well that he can share. The only thing is that they're all in Fortran, so you have to sort of figure out how to compile a Fortran program. So basically, you put in the unit cell parameters at the pressure and temperature of your experiment. You have to put in the single crystal elastic constants, and then you put in slip systems. And the slip systems are like the model parameters that you can change, right? So the elastic constants are the elastic constants and you're stuck with them, but you can mess around with the slip systems to get answers that look like your data. So this is a forward modeling problem. So you have to put in the geometry of the slip system, and you have to put in its critical resolve shear stress and hardening parameters. And there's a little equation that shows how all those go together. So basically, the critical resolve shear stress, which is tau, gets updated as a function of the original critical resolve shear stress, and then the rest of this equation, which is dependent upon shear strain because there's hardening. So you have your list of grains, which is in the Bungo-Euler style, and each grain has its own Euler angles and a weighting factor. So if you have a preferred orientation, you can put in a big weighting factor for the grains that are like dominating the fabric. And then you have to specify the boundary conditions for the experiment. You can either control based on displacement, you can control based on the stress, and then you put in the final stress strain state that you want to arrive at. And the starting point, you can either start from hydrostatic, which is like you don't put in a starting point, but you can also use a previous deformation sequence as your input. And I don't think I'm going to talk about that very much here, but for Taryn's experiments, we go up and then we come back down. So we use we model going all the way up, and then we take the end state at the top of our deformation experiment, and then we use that as a starting point for for basically extending. So what you get out of the model are diffraction peaks. What you have to put in, I'm sorry, you put in the diffraction peaks that you want to model, right? So far we've just talked about it calculating what's going on in the sample, but then the diffraction is what you're looking at. So it contains a group of subroutines that calculate what the diffraction will look like. So you have to tell it which diffraction peaks you want to model, and you want to tell it what geometry you're observing those diffraction peaks at. So you can, put in detectors 1 and 5, you can put in the geometry for detector 2, you can put in 3 different geometries. So where you are around the circle is also specified in the model. And then what you get out is the final stress and strain state for every single grain in your model. You get the macroscopic stress and strain for the entire, incremented through the entire deformation experiment. You get the lattice strain for each deformation increment, and you get the percent activity of each slip system in the situation. So basically, you know everything about what's going on in the model. And the point of doing this is then you compare your model to your diffraction data to see, did the assumptions I built into the model work? So here's an example for phaolite, where we have the little dots are diffraction data and the solid lines are our model. So when we had good luck with quartz in the beginning. It was like, great, this works. And then we tried phaolite. It was a total failure. And the reason is because we did not anticipate that kink bands were going to be a factor in the deformation of olivine. So when we saw this, we noticed that the 002 peak in diffraction was down here. It had been basically something was actively allowing the grains that contribute to this peak to not be stressed. They were relaxing. So they should have gone off like this, oops, but they were down here. So that told us that there was something else going on. So we looked at, well, what happens in reality with olivine is that we get these kink bands forming in olivine at sort of high strain, low temperature conditions. And so this is a known thing. So we basically did an an EBSD study to characterize the crystallography of the kink bands, although it was known, but we just felt like doing it. Anyway, and so then we built a slip system that modified the group of grains that would be candidates for kink bands such that they would be able to relax. And then we put that in our model. And so now here are the model lines like this. And you can see we're able to match that 002 reflection really well. So it allowed us, basically running these models made us realize we were missing something because, you put in what you think is happening and then the model goes, nah, that's not right. So another thing we found is that we were able to take the critical resolve shear stresses for the slip systems in the models that worked, and we were able to compare them to single crystal data. So this is the background plot is from Durant et al. 2007, which was a big analysis of critical resolve shear stresses in olivine. And we just dropped the critical resolve shear stresses from our experiments onto the plot, and they line up really beautifully. So that means that you can get information out of these models about it's like a validation. It's really what's happening. Okay, so here's an example of us fitting a series of data. So here we have, or one experiment, a series of different fits. So here I've just put in the elastic constants and I have no slip systems active at all. So you can see the model kind of goes off into outer space where the sample, softens. This is the yielding, right? Because these are basically stress strain curves. I'm plotting the lattice strain. Oh, I think I forgot to say, on all our plots, we plot lattice strain, which is we take D0 as the hydrostatic d-spacing, and then we subtract that from the current d-spacing. So that's what's plotted on these diagrams. Okay, so whoops, I went ahead too far. Okay, here I want to be. All right, so here's elastic only and our diffraction data. And then over here, oh, okay. Over here, I have added what we call the isotropic system. We found in our experiments, again, an unanticipated deformation mechanism, which is at very low strain, something happens where the sample begins to yield before we get a lot of dislocation activity. So you can actually see that failure down in here already. The elastic model, the lattice strain is higher than we're seeing. So that means our sample is able to relax itself somehow. So we put in this isotropic deformation mechanism to get us a good match to up in here roughly. And then we added next a group of the kink bands and also some slip. And we're able to get the model to really match the diffraction fairly well, which gives me confidence that this is the macroscopic stress for the sample, right? Because we have all of the lattice planes are agreeing with the model. So here's just the isotropic system. We can basically measure the Young's modulus from our resulting models, and we can show the softening of the Young's modulus as a function of temperature. So this one is for olivine. So this is the single crystal elastic constants, which drop slightly with temperature, but the polycrystal, the Young's modulus drops quite a bit. And then over here, I have a similar plot for quartz, where again, we're seeing a considerable softening of the Young's modulus as we get above 600 degrees. Okay, so those are some fun things that we've done, and I want to just go back to, okay, how would you do this analysis? So we plot, as I said, the lattice strain, which is where we're taking D0 from the same detector that we're looking at the d-spacing. So we're not subtracting d-spacings from different detectors from each other, which is what Singh's method involves. We're just comparing the evolution of the lattice strain in a single detector and plotting them all together on a plot. So that's what this looks like when we have our data. We can plot the lattice strain versus time. And here I showed you this group of experiments earlier where I had just the lattice constants versus time. Okay, so there it's basically ready to model once you've done that. And an important thing is to make sure that the time at which you declare your sample to be hydrostatic all of the lattice planes that you're working with agree that they're hydrostatic, because if they're not, that means you've got residual stress in your sample, which makes things more complicated. So the next thing to do, oh, some bad things happened in my slides. Okay, so there's some words in there, but they got smallened. But what you want to do is you want to run some just trial models where you put in the elastic constants and then you put in like a slip system. So here I've run an EPSC model for olivine, and I'm just running the 001100 plane slip system, and I put in a critical resolve shear stress and a hardening parameter, and we just see what they do. And so all of the different lines are different lattice planes. So now if you imagine taking, let's say, 4% strain, and then just making a little plot that shows where each one of these each lattice strain is, and I'm just going to do for the top half, you could compact that little cluster of lines into a single group of dots, which is what I've got over here. And the reason to do this is I've looked at a whole bunch of different slip systems in olivine. There are 8 in olivine. And I've plotted the strain, the lattice strain in the compression direction for each one of these different slip systems without changing the critical resolve shear stress or anything else. Just the only thing I'm changing is just the slip system. And then what I can do is I can look at the lattice planes that that I can measure, and I can see, well, can I tell the difference between the operation of 100 slip on the 010 plane and the 100 slip on the 001 plane? And the answer is yes, you can. Because if you look at the 120, it's got a very small lattice strain compared it's very different rather from the other guys, which are plotted clustering here. And then, I'm sorry, I said that all inside out. Anyway, so we have a bigger lattice strain for the 120 than we do for, let's say, the 101 or the 021, etc. And then when we look at the 100 slip operating the 001 plane, you can see the 120 is up here, whereas the 101 is down here. So basically, if you do this ahead of time, and it's not a big deal, you just run 4 or 5 models, and models take 10 minutes each to run. You get an idea of whether or not each different slip system gives you a different looking pattern in your diffraction. Another thing we did, and it's easy to do, is you look at how does the critical resolve shear stress and the hardening parameters impact your model. So here is a single slip plane, and I'm keeping the hardening parameters constant, but I'm busy changing the critical resolve shear stress for each one. So this is the purely elastic 101 peak. And then I've given it a high critical resolve shear stress, so you can see it comes up here, and that it gets to a certain point. It's exceeded the critical resolve shear stress, and then you can see that the line trends off this way. Whereas if your critical resolve shear stress is a tenth smaller, then you get it's elastic down here, but you have yielding much earlier, and you see the lattice strains don't increase as rapidly, right? So once you've run some basic simulations, then it gives you an idea of how to make your model look like your data. So we collect all our data from this is the same experiment we've been looking at all along. I've now got lattice strain, and now it's sample strain on this axis, and instead of time. And then what we do is we put in all the parameters into the model, and we just run an elastic model, and then we add the pieces. And I think I showed you this for a single one before, right? So we did an elastic model, then we decided we needed some kind of isotropic model to add to that, and then we add in the kink bands and slip. And the the way we get them to act at different times is by giving them different critical resolve shear stresses. So here's the whole suite, which we have modeled now, all of our experiments. And this is part of the data set that gave us the critical resolve shear stresses that we could match to the literature. Okay, so basically my kind of little advertising here is that the EPSC is not super hard. It gives you a single macroscopic stress rather than several. I showed you this diagram before. So there is one macroscopic stress that allows the sample to have all these different stresses in different grades. And it allows you to learn about deformation mechanisms within your sample. And the other thing it does is that you can avoid questions about friction in your cell. So this is a group of stresses from our EPSC models for an experiment where we had olivine being pushed on by an alumina piston. So the piston is this round round symbol here. And simultaneously, this is the stress in the forced-right. So the forced-right and the alumina are pushing up against each other. And you see that they match each other really well until the forced-right really begins to yield. And so the forced-right goes off this way, and the alumina piston, which would be our stress gauge, continues to get to higher stresses. So there are friction things going on inside your cell, which make it more desirable to get stress out of your sample than some other part of the cell. So this is just the same thing at a different condition. Early on, the piston and the sample agree, but as the sample yields, the piston records increasing differential stress. And it's unfortunate that we seem to see this. I don't think I'm the only group, or we're not the only group I'm not a group. We're not the only group who sees this kind of thing. And if you can't get diffraction out of your sample, you don't really have a choice. But anyway, if you can get diffraction from your sample, it's good. And then the last thing is that, remember going all the way back to the start, that the transverse detectors and all the other detectors, they're taking in this really complicated average of a complicated set of grains that don't have a lot in common. So as you have grain growth and stuff going on in your sample, those detectors tend to get noisier. So here you can see in the transverse detector, the 140, it comes down and then it pops up and it drops down again. And the little crosses for the 112 are also kind of nasty. Here you can see the green, which is the, why is the green? Oh, I see. It's the 130. The 130 is going up and down in a sort of inconvenient way. So if you're subtracting your transverse detectors from your compression detectors, you're taking this chaos and you're kind of inserting it into your data. So when we do our fits, we really focus on the compression detectors to make sure that the fit is best up here. And then we don't worry as much about, individual peaks matching because they do go up and down. And so I find that that's kind of very useful for us. Okay, so I'm done. Are there questions? And then I guess Karen is ready to go.
Well,
Yeah, I have two quick questions.
Yeah.
One is how many peaks do you need to get a macroscopic stress that's constant? For example, if you choose 5 peaks or 3 peaks, 7 peaks, what is the minimum peaks do you have to achieve that constant stress, let's say?
You probably want 3 peaks, I would guess. I've never really tried
Okay.
to, I mean, if you had 1 peak, you can always model that peak and it will tell you what it thinks the other peaks are doing, but you can't at that point, well, less data is worse. That's what I would say. You know, you can,
Okay. So my second question also
Yeah.
with the EPSL. Let's say if we want the user to use it like very handy on the beamline or when they process the data, you said it's right now just Fortran program, right? Is
Yeah.
that possible for something like user can handle easily as long as they have data? Let's say it's a lattice string, all those they put in, they can start to play with it without too much problem.
Yeah, I mean, it's just a matter of having having the code compiled. Because you guys on the Beamline, you run PCs, right? And so you right now I'm struggling with my Mac, not wanting to, you can get a Mac to run a Fortran code, but it's a little bit ugly. But PCs, it's a really old code. It's very stable. And I don't think there's a reason why you couldn't have it running on the Beamline. It's just that how can I put it? It's like we usually go home and process our data, right? So um, get our sample strains and everything. So it's kind of something that you do when you have a pretty good handle on what your data looks like.
Yeah.
They probably translate Fortran to Python using AI these days.
Yeah.
Yeah, I was thinking about that. I think, was it Matt? Somebody told me, oh no, it was Sebastian. He said, no, don't try to translate into Python. That's a miserable job. But I had a student who was tinkering with kind of getting a Python code to run the Fortran and feed it different slip systems to see if we could because you kind of have to, try a given critical resolve shear stress and say, oh, that doesn't look very good, so you're going to try another one, right? So there's a little bit of iteration that you have to do this. And so we were trying to get a kind of wrapper, a Python wrapper that would run the Fortran code and then calculate the difference between your model and your peaks. But I think I'd need to get a grant to do that just because it's
That'd be
not
great.
it's not a volunteer job.
Because I feel your promotion for EPSL is good because they can see the mechanism, all those. That's extra information you can get from the feeding. So I feel that's really good. On the experimental side, right now there are quite a few users trying to avoid this problem experimentally. So by using the pressure gauge that's isotropic. Let's say, like for low pressure, somebody use salt, which is cubic and isotropic. Another one they use is Perl. So far, they kind of all the peaks gave you the same answer after stress. Not like when you use olivine or alumina, each peak gave you a different answer. So this is the theory solution for this problem and also experimental solution for this problem. So you can go either, but I feel I like the theory solution because they give you extra information.
Right. The thing is, if you use a stress gauge, you might want to have several of them, like something at the top and the bottom and the middle. I don't know because
That's what people do. They do a
yeah.
middle and either top or bottom. Yeah.
Mm-hmm.
Because
Yeah.
they take up the length. Yeah.
Okay. Yeah. Any other questions?
Yeah, how applicable are the self-consistent model and the ETSC code to other type of loading conditions? Like, could we use it for a bending test analysis, or would it be not
A what?
applicable?
I'm sorry, a what test? I didn't hear.
Some,
You mean shear or bend?
I
It
mean,
says bending.
some
Bending.
Engineering studies, they often do beam bending, right? And
Oh,
I'm not necessarily bending, but anything other than the DDF.
The actual load or biaxial.
Um,
That's your boundary condition. As long as you
yeah,
describe the boundary condition, you should be okay.
right. Because you can put in it, you have to put in the sort of full stress tensor. Basically, if you wanted to control by stress, you have to put in the whole stress tensor. We typically run in displacement and let the stress be what it's going to be, and then we specify uniaxial displacement. But you can run by just stress control. So like when we're decompressing, I guess I have one here. These are from Taryn, as where she runs a compression experiment, and then at the end she decompresses, and we have this model that runs along the straightforward part, and then you'll see, well, here there's a point. That's like where the little corner, that's where we implement a second model, and here we're using stress as the driving factor, and so we're just decompressing. We're bringing things back down to zero. And this is another thing, as you can see in the experiments, all the peaks don't go back to zero lattice strain. They're all over the place. So that by the time we've done a full kind of compression and decompression cycle, we have all kinds of residual stress in the sample. So the stress state is really quite complicated, which is why we anneal.
I think it's probably because in this model, you actually don't consider possible grain overlap, because every grain was treated like a ellipse. So you don't actually consider nearest neighbor interactions. Whereas in the real world, in the real world, you have near neighbor interactions that can drastically change the stress state.
Yeah.
Actually.
Although if you had anything that you're going to see in diffraction is an average of a lot of things, right?
Yeah.
So in terms of the diffraction, the diffraction does not come back to a single place, right? It's just sort of a mess all over the place, which means that different groups of grains are doing different things, and there are enough of them to give you a diffraction peak that's different from that gives you a different lattice strain.
All right, so I'm just going to provide a brief overview of processing an ultrasonics file collected during a 6BNB experiment in plot LVP. And so I'm sure this has probably been floated around, but the information that I'm providing on the ultrasonics instruction can be found in the plot LVP PowerPoint on the same website where you can download the executable as well as the grfont.dat file. And so the diascope is the acoustic system at 6BNB that's used to obtain the two-way travel time measurements during the experiments. On the right here, I am just showing a schematic of the cell assembly sitting atop the lower tungsten carbide anvil, where we have the single transducer attached to the lower anvil, which allows us to propagate either a P or S wave signal through the cell assembly. And as the wave hits the interface between two different materials of varying acoustic impedance, part of the wave energy is going to be reflected as the wave continues. And so at each interface between the different materials, the wave energy will be reflected, and the diascope output is something like we have here on the right, where we have these varying reflections which are marked as the interfaces between the different materials. And so we can use the pulsed echo overlap method to, we can use the pulsed echo overlap method to take the reflections for a given material along the path. So if we want to determine the two-way travel time within the sample, in this case, we would use the reflections R2 and R1 from the output, and we can determine the time offset between those two reflections to determine the two-way travel time for the sample. And we can use these two-way travel times in conjunction with the sample length measurements you obtain from the radiographic images to get the P and S wave velocities during these experiments. And as I mentioned, a lot of this data is pulled from the Plot LVP PowerPoint, so we're just going to walk through the various steps from importing a file to processing the file to extract the two-way travel time. And so to get started, you need to have your Plot LVP executable as well as the ultrasonic files you want to look at, and then the grfont.dat file, the same font file that's used in diffraction processing. And if we were to open up one of these files, you can see some of the text information here. We have a collection time of 20 microseconds in this file. The frequency that we optimized for was 35 megahertz, and so this indicates that we're looking at an S-wave ultrasonics file. Our input signal was a 5-cycle sine wave, noted here, and these are the values from the log file during the experiment when the ultrasonic file was collected, and then our output is the one waveform. These are the data points that we'll use to visualize the summed waveform in Plot LVP. So I'm not sure if you guys have opened up Plot LVP yet, but when you first open Plot LVP, you have a main graphics window in white, as well as a yellow text window. And for ultrasonics data processing, you're focusing only on the ultrasonics tab at the top. And when you first select the ultrasonics tab, you only have two options initially available: import ultrasonics raw data and get scale shift factors. So if we go and select the import ultrasonics raw data, we can select our initial file from the directory that will open up. Upon doing so, the main graphics window remains blank until we read in the file. So going back to the ultrasonics tab, we can select read. When we do that, going back to the ultrasonics tab, plot waveform will populate, and that will allow us to visualize the full waveform in the main graphics window. The other tab I just wanted to mention that is populated initially is this get scale shift factors, and this window will just open up showing the different scaling and shifting factors that are used in performing the overlay of the reflections to get the two-way travel time. And so when you open up your waveform, there's some information listed. As I mentioned, this is a 35 megahertz frequency example. So we're looking at an S-wave signal performed over a 20 microsecond collection time. And then in the bottom left-hand corner, we can see that the file that we've loaded in. And our plot is of intensity or amplitude of our reflections as a function of time. And since this is an S-wave file, we want to focus on this middle section here of highest amplitude. And to see this region a little bit better, we can zoom in using the hotkeys L and R. And so you want to basically place your cursor to the left in the main graphics window, select L, move your cursor to the right-hand side, select R. That'll allow you to zoom in and see the reflections that I showed on the previous slide, indicating the various interfaces that the ultrasonic wave is intersecting along its path. And so to focus on the sample reflections, we can zoom in again using L and R on this region, and we can see now the two reflections that we're going to use to overlay and get our two-way travel time. So to select individual segments, I should mention, once you get to the point where you're happy with the window you've zoomed in on, you have to select Q, the Q key, to stop the option of basically zooming in and allow you to proceed to the next step of selecting the individual segments that you'll use for the overlay. So once you select Q, when you go back to the ultrasonics tab, select segments will now be an option you can choose. And so we're going to go ahead and select segment 1. Since this is a 5-cycle sine wave, basically you just want to give yourself a little bit of room prior to that waveform or the reflection. And you can use any key to select a segment. I typically use the space bar. And so using the space bar, select the left edge of that segment, move your cursor to the right, select the right edge of the segment, and you've selected your first segment. Going back to the ultrasonics tab, you can select segment 2, and for segment 2, the the return is the same width as segment 1, and so you will only choose the left side of the region of interest. And so you have to keep that in mind. If for some reason you need to look at a wider region for segment 2, you want to expand the width of your segment 1 region. And so you'll press the space bar on the left-hand side of this reflection, and now you have segment 2. And so to plot both of the segments on the same graphic, go back to the ultrasonics tab. Plot segments is now an option. And here we have our segment 1 in black and our segment 2 in red. So the bottom interface of the sample, the top interface of the sample. And to overlap the data, or to overlap the two reflections, there are various hotkeys. And again, these are all listed in that plot LVP PowerPoint. For scaling and shifting the reflection, the reflections to get the overlay. And the output is something on the right like this, where we have our red segment, the second reflection, overlaying the first reflection. And the result is a travel time noted in the top right-hand corner. For this example, we had a 0.5384 microsecond travel time. And one thing I just wanted to note, basically getting to this final point, we'll just quickly walk through that. As I mentioned before, the acoustic impedance decreases, or the acoustic impedance difference between two materials will dictate the percentage of the wave energy that's reflected and the percent that's transmitted. And so in our transitioning from the anvil to the cell, we have a decrease in acoustic impedance from the anvil to the aluminum buff rod to the sample. But above the sample is an upper aluminum piston in the cell assembly that is the same material as the lower aluminum buff rod. So we're actually going up in acoustic impedance. And this requires a inversion of the reflection, so basically a 180-degree phase shift. And so I'm just going to basically walk through inverting that second waveform before we do our final overlay. So back within the ultrasonics tab in the Get Scale Shift Factors window, you basically just need to apply a negative scale factor to the upper box to invert the red segment, the second segment. And then you can proceed with the inverting of the overlapping of the waveform. So you have your initial waveform. Once you've walked through ultrasonics plot waveform, you can invert the second segment using the hotkeys plus or minus. So that'll put the red segment below the x-axis. I then like to basically scale both of the segments positively. Segment 1 uses the square brackets to enlarge or to scale, and then segment 2 uses the plus and minus keys. I then will keep basically the second segment inverted and shift horizontally using the caret keys of segment 2 to align with segment 1, doing a rough alignment, and then proceed with the final vertical alignment of the waveform with the red second segment overlaying segment 1, producing the time offset, the two-way travel time in the upper right-hand corner. And with that, I'll just leave the instructions that you can find in the plot LVP PowerPoint. I know that was a little fast, but hopefully that provided enough information. I'm sure Matt can answer any questions.
That's great. Thank you very much.
Thank you.
Questions? I guess we haven't got to that part.
Yeah. Jumping ahead. All right.
Okay. Thank you, Gary.
Mm-hmm.